and control for Aedes mosquitoes and dengue vectors has been and continues to be essential to fight dengue, and we need more effective, proven vector control methods. Wolbachia-mediated population suppression, or Wolbachia suppression, is a technique in which male mosquitoes with Wolbachia are released to mate with wild female mosquitoes. Because of cytoplasmic incompatibility between the sperm and the egg, after mating, the female mosquito can lay eggs, but they don't hatch, resulting in progressive reduction of the mosquito population over time. Previous results of the use of this technique in Australia, the United States, and Singapore had shown reduction of mosquito populations ranging from 72 to 99%. The Communities Organized to Prevent Arboviruses, or COPA, is an ongoing research study in Ponce, Puerto Rico, established in 2018, and it's a collaboration between the Ponce Health Sciences University, the Puerto Rico Vector Control Unit, and the CDC's dengue branch. We collaborated with Verily for this specific project. COPA is a prospective cohort. We seek to determine the incidence of arboviral infections and assess the burden and etiology of acute varicose. About 3,800 participants, ages 1 to 50, are followed every year. They answer a standardized questionnaire and provide a blood sample for arboviral testing. Participants are residents of 38 distinct clusters, so we had a cluster randomized trial design. We have assessed and we continue to assess vector control methods' acceptability before the implementation. For the methods, the pathogen and vector targeted are dengue and Aedes aegypti, and the human population is the COPA participants that I just described. The intervention is a release to prevent mosquitoes with Wolbachia. There is no intervention provided in the control areas, and we were looking to evaluate both the reduction of female mosquitoes and the reduction of human infections. We started the educational campaign in June 2020, and 3 months later, releases started in 19, or half of the study clusters. Female mosquitoes were monitored with 604 AGO, algocidal rabbit ovitraps, traps. And in the map, you can see the location of the 38 clusters of the study. The intervention clusters are in blue, and the control clusters are in pink. Mosquitoes were reared and parked in the Verily facility in San Francisco. Were shipped by air with a connection in the mainland U.S. They arrived in San Juan and were driven to Ponce, about 1.5 hours by road. They were unpacked, distributed into tubes, and then released using Verily custom feeder banks. Releases occurred in 19 clusters for about 4 months. In December 2020, preliminary analysis showed that suppression levels were suboptimal. It was decided to start a phased implementation, starting with 4 intervention clusters, to be able to increase the overflowing ratios in these clusters. These are the ratios of male mosquitoes with Wolbachia to wild male mosquitoes, with the intention to then move to the next 4 clusters and so on. Releases occur in these 4 clusters, with 4 clusters as controls, for about 12 months, and we do not expand to additional clusters, and we will see the results. The releases of mosquitoes ended in December 2020. In the map, you can see again the intervention clusters in blue and the control clusters in green. For determining the mosquito population suppression levels, we used a generalized mixed model using weekly trap counts of female Aedes aegypti to obtain the ratio of mosquitoes counts in intervention to control clusters. During the study, different assays were used to determine mosquito characteristics, to calculate the overflowing ratios, and to evaluate optimal shipping conditions. So what were our results? There were no dengue cases detected by molecular testing in our cohort during the study period. This is consistent with the data available for active and surveillance data in the region. We detected one participant with a positive serology test, gender, in an intervention cluster. So we had very low data transmission and insufficient data to assess humanity. What I'm going to show you now is the epidemiological. These are the numbers of mosquitoes in millions released per week. 26 million mosquitoes in total were released. Mosquito sheep are shown in green. Mosquitoes released in orange, and mosquitoes that arrived at expected time in the dashed line. 35% of shipments were compromised, resulting in 36-hour delay per month. When working in 19 clusters, we were releasing about 1 million mosquitoes per week, and this increased to an average of 2 million mosquitoes per week after we moved to only releasing 18 clusters. This graph shows the mean number of female mosquitoes per week on the y-axis, the control areas in purple, and the treatment areas in red. Before the dotted line, we were releasing in 19 clusters, and we see little difference between intervention and control clusters. They overlap. After the releases in 4 clusters, you see a little separation that started in March, and about 3 months after the start of the releases, you start seeing a bigger separation between the 2 lines. The separation between treatment and control continues until we stop the releases that happened in December 2021. This is the second dotted line. And in the graph below, you can see the total rain in millimeters from the 3 environmental stations available in the area of the clusters. The raises and the falls in the number of mosquitoes follow the rain patterns very closely. And in this graph, you can see the y-axis is showing the estimated ratio of female Aedes aegypti counts in the intervention clusters versus the control clusters. The x-axis is showing the time period starting in January 2021 when releases started only in 5 clusters. The dotted vertical line shows when releases start, and the ratio is less than 1, shown below the horizontal gray line, meaning that the intervention clusters had a significantly lower count per trap per week than the control clusters. This is after we adjusted for confounders like temperature, rainfall, and humidity. On average, over the intervention period, we found that Aedes aegypti counts in the intervention clusters were 51% of counts in the control clusters. After the releases stopped, the mosquito population rebounded to levels similar to the control clusters in about 2 to 4 months. So the suppression levels were lower than what we expected, and we investigated extensively during and after the study the potential reasons for these results. And I'll show you some of these investigations. So maybe there have been releases of female mosquitoes with Wolbachia that could have resulted in the establishment of Wolbachia in the mosquito population. That was the reason why we were seeing lower suppression. So we collected larvae and tested them for the presence of Wolbachia, and we did not find any positive results. We did not find evidence of accidental female mosquito releases or Wolbachia establishment in the population. So what about the fitness of the mosquitoes that we were releasing? The shipment containers were developed for this specific project and were continued to be optimized during the duration of the study. On the y-axis in this graph, you can see the measure of mosquito fitness, that is the proportion of wild female mosquitoes that mated with Wolbachia males, and the different vessels are on the x-axis. To conduct these experiments, 10 males with Wolbachia that had been packed and shipped, 10 wild males and 10 wild females were placed in a cage and allowed to mate. With 50% of females mated with Wolbachia males, they were considered as fit as the wild males. And the graph shows that earlier versions of the vessel were not that good, and there were improvements along the way. Most of our shipments were done with the version 3.1 in red, and it was a good vessel that had some durability. This is the same experiment comparing fitness for freshly reared mosquitoes and not shipped. Mosquitoes shipped on time and mosquitoes that were delayed. We know that shipping mosquitoes have a fitness cost, and these experiments with delayed shipments suggest even a greater fitness cost. What about the number of mosquitoes being released? Overflowing ratios are shown in the y-axis and time on the x-axis for each of the treatment clusters. Most ratios range from 5 to 20 and were considered adequate based on previous experiences with Robakia suppression in other sites. However, there was a lot of temporal and spatial heterogeneity, and in some clusters there were traps with consistent low overflowing ratios. These overflowing ratios were probably not enough to compensate for the fitness cost from packing and shipping. And there were persistent islands with high mosquito counts. To the left there is a heat map showing weekly human mosquito counts from AGL traps, and to the right there is the geographic location for these traps. The traps in the middle are in a public housing complex where the banks could not access to do the releases, and while there was good control around them, there were few traps in the center with high counts. In response to this challenge, we did some adjustments like the second releases by hand walking in these communities. Sorry. So in summary, we were not able to evaluate epidemiological impact of Robakia mosquitoes releases due to the low transmission of dengue. We modified the study and we went from 19 to 4 clusters to respond to the preliminary findings of suppression levels. We were able to improve packing and shipping methods, but more work was and is needed. The counts in intervention clusters were 51% of those in control clusters on average, despite similar overflowing ratios to previous studies. We modified the releases to improve mosquito numbers, distribution, and fitness. And we think that suboptimal suppression levels were due to a combination of many factors, but most likely reduced fitness after long shipping. And I want to finish the presentation recognizing all of these amazing collaborations and teams that worked hard for this study to be implemented. It was the first Robakia-based technique in the Caribbean, and our cohort, our Copa Cohort Continue, we are now in the 4th year. We have several activities out there these days that you can check out, and all of that thanks to the tremendous amount of work of these professionals in the field.
Thank you. Time for 2 questions.
Yeah, hi. Nice presentation. My name is Mamadou Koulibaly. I'm coming from Mali. So since we've got some impact of shipping on the fitness, is building capacity, infrastructure capacities on site an option to deal with that?
Not right now, but in retrospective, in hindsight, it would have been very nice to have a local factory, and it was one of the options that we had thought at the beginning, but given some challenges in funding, it was not possible to have a local factory. We had to rely on the factory in some cases. But yes, that probably help a lot.
This biological control measure is interesting. Do you have confidence in it? Should it be done or pursued? The next question is, in the release of the male mosquitoes, how were you able to control the range to which they flew? Thank you.
Thank you. We still think that Wolbachia suppression could be a very useful tool in combination with other tools for vector control. The population of mosquitoes in Puerto Rico is impressive, and we now know that Wolbachia suppression by itself is not capable to do it. But we still think that it's a tool that could be used with other methods to control Aedes aegypti. The second question, we didn't have any. Yeah, they can fly. Yes. So Yeah, so our cluster were designed in a way that we try to diminish the risk for mosquitoes to, contaminate other clusters. And so we had certain geographical barriers and other handmade barriers and try to make sure that, they're not a control cluster next to an intervention cluster as much as we could. So no, we could not control that. We did some analysis trying to think if there was some effects of mosquitoes flying in or flying out, and we couldn't tell that that was one of the reasons that why the suppression levels were lower than expected.
Thank you.
To get in there and know the number of female mosquitoes in your experimental design. Don't you think that this is a best way to conduct the work?
We only release male mosquitoes, and male mosquitoes have been released before in many different areas. So we were building on the previous work that were done that demonstrated suppression.
Discussion can continue later. We are out of time.
Thank you. So Magellan is our next speaker.
I am Mazaran Chakri, a research scientist at French Center for Research in Infectious Diseases in Cameroon, in the Charles Wanji Research Group. I am working mainly on resistance management and also molecular basis of resistance to novel insecticides. Today I'll be presenting on the efficacy of coconut-based nets, G2, on malaria vectors in Cameroon. Okay, here is just to show that from 2000 to 2015 have been a significant reduction in malaria burden, mainly due to the scale-up of bed nets. The objective is still here, we are like off target of the global vision of WHO to eliminate malaria by 2030. And this is mainly due to the scale-up or escalation of resistance to pyrethroid integrated bed nets. So in regard to the challenge, we have here a toolkit to minimize this situation, but bed net remain the core intervention, and we are having some innovations in bed nets where we have nets combining other ingredients than only pyrethroid. We have the case for Interceptor G2, which is a cofenapi-based net, and also wire guard, which contains pyriproxyfen. So for Interceptor G2, the efficacy has been proven in many countries, Benin, Burkina Faso, Tanzania, and Ivory Coast, both on Anopheles gambiae and Anopheles finestus. So this net, as I said, it contains alpha-cypermethrin and cofenapi. And in Cameroon, we had no information on the efficacy of these tools, and it was planned for the malaria campaign of 2022-2023. So we wanted in this study to evaluate the efficacy of the tool compared to PBO and standard nets in some of the locations. Here in blue are locations where they plan to use Interceptor G2, but we had no information on the efficacy of the tool in those locations. So we just learned that just based on the level of pyrethroid resistance, which are very intense in those locations. So what we did was to conduct experimental hot trials in 2 locations. So you have experimental hot stations in 2 locations. In Olenge, where you have a very moderate level of resistance to pyrethroid, and in Nebelong, where the level of resistance to pyrethroid is very high. So we conducted experimental hot trial in both locations, where we used wire sentry as a standard net, permanent tree as a PBO-based net, Interceptor G2 and wire guard as next generation nets, and sleepers. They spent like 36 nights in these huts, and you are rotating the tools weekly just to avoid any specific bias from the attractiveness of the sleepers. And then you collected their live and dead mosquitoes, and you measure the deterrence, the filling rates, the mortality, and the blood season for each net, and you compare among these tools. Also, you genotype their live versus death, the blood fed, and those exiting the room. There's some molecular markers just to see if we can have like potential contributions of resistant markers to the failure of this tool. Because we have experimental hospitalization only in some few sites, so we collected also larvae and adults in other sites to conduct a contest and parent assay with this net, and also crossing the field-resistant mosquitoes as molecular markers. Most of them are fixed with the susceptible lab strain to genotype some of the markers and make a link between all those phenotypes and the presence of the resistant markers. Here we have the level of susceptibility to various nets. Here we have the lab strain Kisumu, where all the nets show like very good efficacy with optimal efficacy. So most of them, but when you move to the field strain, both Anopheles sinensis and Anopheles gambiae in Conasay, you notice that the mortality was very low for standard nets and even the next generation nets in contest. Only PBO nets show a very good efficacy in both sides. Now coming to experimental hot trial, what we notice is a very high efficacy of Interceptor GT nets with very high level of mortality compared to other nets, even the PBO nets, which is permanent 2.0. So the 20 wash and 0 wash of Interceptor G2 was most efficient, and even the personal protection rates, which is the ability of the nets to protect the sleepers from the biting of mosquitoes, was very high for permanent Interceptor G2 and wire guard. But surprisingly, we conducted the same one in Libelon. As I said earlier, the location is you have very high level of resistance to pyrethroids. And you can see here the level of mortality to Interceptor G2, where you compare various prototypes of IG2, where you have prophenapy on whole nets on site and on top. So for all the various combinations, we are having very low mortality compared to Elende, where the mortality was very high and consistent compared to the previous study we conducted. So we wanted to see here what could be molecular drivers of resistance to this net in a location like Libelon. And we have a PhD student in our group who detected like a mutation on 91 gene and showed that the mutation was significantly associated with pyrethroid resistance. So we wanted here to see what is the contribution to the failure or to reduce susceptibility to Interceptor G2. And you can see here that most of the alive mosquitoes, they have these resistant markers compared to all the deaths, showing that this marker potentially is contributing to the low efficacy of Interceptor G2. And you notice that in Libelon, the frequency of this allele was very high, very close to fixation. Whereas in, going back to 2016, we had like very low level of this mutation, showing that the selection is very high. And that in locations where you have 91 resistance, the efficacy of Interceptor G2 could be jeopardized. And you have here the ratio comparison between homozygote resistant mosquitoes, heterozygotes, and the susceptible for the ability to survive exposure to this net. In the case of Anopheles gambiae, where KGR is mainly fixed, so what we did here was to cross field strain from Colendum, which is a location in Cameroon where the level of resistance to pyrethroid is very high, with the susceptible lab strain. And then using the IV strain, we did a tunnel test, and you can see here the level of mortality after tunnel test was very low, but at least the IG2 was showing a greater efficacy compared to Interceptor alone, although the difference was not significant. And what we saw was that even for the KGR, the association was very high of having these markers and the ability to survive IG2 exposure. Although we showed previously that the KGR is negatively associated with prophenapy resistance. So this might be probably due to resistance to alpha cytometry, which is reducing the efficacy of the tool. So what we can say here is that Interceptor G2 was very efficient on Anopheles sinensis from Elende, and permanently also was very efficient, whereas the pyrethroid only met lost drastically the efficacy. IG2 show very low efficacy on Anopheles sinensis population from Libelon, which is an area with very high parental resistance. And this is partially due to the micro-1 marker as we saw. And also cage-resistant mosquitoes, they display greater ability to survive interceptority exposure compared to the susceptible. And what you can take home as message is that before implementing all these moving nets in locations, you need to really to establish the level of or the performance on local populations. Just don't go with all the locations with the bed net without clear assessment. And for IDT, the best approach to evaluate that is to use experimental hot trials, because in the context, let's say like is that the best option to evaluate the efficacy of the tool. And also for all the other nets coming, we need to define data resistance management plan like rotation to anticipate potential failure of the tools. So I would like to thank all the paid team here and all the collaborators as well as the founders of the project. Thank you so much.
Thanks very much. Plenty of time for questions.
Thank you very much, Magellan, for a very nice talk. I'm just wondering, in the site where you have very low efficacy of interceptor G2, do you have an idea what's the level of expression of the P46P9A is?
Okay, thank you so much.
RNA-seq data or competitive PCR data?
Okay, that study we need to conduct it in areas like Southern Africa, because in Cameroon we do not have like high expression of 6.9A and B. But for other like the Carbacillus esterase and other P450s like the T25A, they are highly overexpressed in the locations.
Vincent Corbel from IAD. Good presentation. Do you think this is CYP9K gene can detoxify the chlorofenavir, for example? And did you plan some validation studies also to transfer?
Thank you so much.
Thanks.
Very interesting question. So after doing this, because the net is combining alpha site and chlorofenapyr, so what we did was to perform an assay differently with alpha site and chlorofenapyr and evaluate what is the contribution of the market to each of the insecticides. And we noticed that the level of association with alpha site was very high, whereas for chlorofenapyr it was a bit moderate.
Thank you very much for your presentation. I'm a data from Nigeria. I've seen the demonstration of molecular tools and characterizing mechanisms of resistance, especially in areas where you have high drug resistance. And I know as scientists, we're supposed to define vector control managers and the options. So in your own candid way, how would you advise the NCP in your country, and the best way to manage an informed decision in terms of choice of method of vector control intervention? Thank you.
Thank you so much. As I just presented, the first thing to do is to test the efficacy of the tool against the local population. Once you notice that the tool is efficient, you can implement it. Now the best management plan, rotation is an option, but it's still unknown how should we rotate the tools. From which one should we rotate? How long should we wait before rotating the tools? So those informations are critical before implementing like rotation or mixture of insecticides. So you have like rotation and mixture, which is very good for management.
Any other questions?
Hi, thank you for the presentation. Maybe I missed, but I saw that you checked for molecular marker CYP9K1 on Finesters, but have you checked the same level of expression in Gambia sensu stricto?
Thank you so much. So in the case of this study, in the location where we worked, we were not able to connect Anopheles gambiae from the experimental hots, because the experimental hots are mainly from the Anopheles finensis, where we have many Anopheles finensis. But from RNA-seq data we are having in Cameroon, the 91 is overexpressed. But for now, we don't have a clear molecular marker to detect that and make an association between the phenotype and the genotype of mosquitoes.
KDR influences?
No, KDR absolutely influences. That's why we assess that early in animal.
Okay, thanks very much.
We are going to introduce the next one. Suleiman Ibrahim Sadi, the molecular drivers of insecticide resistance and the Sahel-Sudanian populations of malaria vectors.
Thank you very much, Majala. Good afternoon, everybody. My name is Ibrahim. I am academic staff in Bayero University, Kano, in northern Nigeria, and I'm here to talk about part of the work I have done during my Wellcome Trust training fellowship between 2017 and 2019. The fellowship was sponsored by the Wellcome Trust, and it was supported by the Center for Research in Infectious Diseases in Cameroon and the Liverpool School of Tropical Medicine in the United Kingdom. So I will talk about the Sahel. The Sahel is a sort of a geographic belt which spans East and West Africa, and which is characterized by high seasonal malaria transmission. It represents the northern transect of malaria endemicity. And if you look at the map, to this side, you can see in the Sahelian region of some countries like Nigeria, Niger, and Chad, with respect to research on malaria vectors, the Sahel region is not far behind compared to the more humid western part of the countries. So this is why we decided to do this work, to target this particular region, to know more about the major malaria vectors in it. So since the Sahel region share similar ecoclimatic conditions, we were thinking, is it possible within the rainy season, which coincides with a peak malaria transmission in the Sahel, whether there is some particular major malaria vector which predominates, and if we can find information, if there is a common mechanism, or there is some, in terms of transmission profile, insecticide resistance and molecular markers of resistance. If they are common, then we can provide such information to control programs, and it will be beneficial. And if we find information with respect to the Sahel, then will that foster collaboration and more coordination and crosstalk between respective malaria control programs in the regions where we have the Sahel. So with this, we decided to go in and do collection in the Sahel region of Nigeria, Niger, Chad, and Cameroon. And we use different ways of collection to minimize any sampling bias. But with the exception of, I think, single sites in Chad, what we have observed was we always collect Anopheles colloxi. We do not find much of Anopheles arabiensis and Anopheles gambiae. And details of insecticide resistance, plasmodium infection, and resting behavior of the mosquitoes we collected have been published in most of our studies. What I will discuss today here is more the molecular work which we have done. So the second aim of the project was we wanted to find out if the molecular mechanism of insecticide resistance in the Sahel is more common than as expected. So to do that, what we did was we took insecticide resistance mosquitoes. These are mosquitoes which survive exposure to delta methane from all the 4 countries, and we use them to do RNA sequencing. And as you can see from this principal component analysis, initial analysis just looking at the data, this is from 500 most variable genes from each, from all the treatments from the 4 countries. You can see the data from the field sample cluster closer together compared to the data we obtained from the fully susceptible population of Anopheles colizei, which is called Inguso, which is fully susceptible to all kind of insecticides. And when we did the differential gene analysis, we found that the usual suspects, cytochrome P450s, carboxyl esterases, and glutathione S transferases, commonly overexpressed across the Sahel. Most importantly, we find these 2 genes, cytochrome P450, SAB6Z2, and glutathione S transferase, GSTE2. They were the most consistently and commonly overexpressed genes across the Sahel region of the 4 countries. And to validate the qPCR data, we selected 12 genes with high overexpression and high mean expression level, and we found that there is positive and significant correlation between the qPCR data and the RNA sequencing data. With the qPCR data confirming that SAB6Z2 and GSTE2 are the most overexpressed genes in all the samples from the 4 countries. And then next what we did was we, for functional validation, we introduced 6Z2 and GSTE2 into transgenic flies, and we screened the flies for resistance phenotype with different kind of insecticides. So as you can see here, for SAB6Z2, we saw that it can confer marginal resistance to alpha-cytokine, and it can confer also some resistance to phenoxybenzyl alcohol, which is a primary product of pyrethroid hydrolysis by carboxyl esterases. And surprisingly, we saw that when we exposed flies containing SAB6Z2 to clothianidin, we saw higher mortality with experimental flies compared to control, which at some time 3 hours and 6 hours of exposure is statistically significant. And this suggests that possibly SAB6Z2 is bioactivating clothianidin into more insecticidally active intermediate which kill the flies. And this was why I was asking Magellan also, because in lab we've seen that SAB6B9A can metabolize chlorophenol, and this is why, and maybe possibly into more insecticidally active intermediate. And this is why I was asking him if they see SAB6B9A is a place where they have a high resistance to interceptor G2. And then we sequenced 4 genes, including carboxyl esterase, GSTE2, SAB6Z2, and UGT. We did not find, contrary to the situation with most resistance genes in Anopheles plastis, we did not see mutations in the coding regions of the genes. And because of that, we decided then to look into the regulatory element. So that's the 5' UTR regulatory element of the gene. So I am only going to talk about the GSTE2 here. So we took 10 mosquitoes, 10 female mosquitoes, each alive, 10 alive and 10 dead, from each of the 4 countries, in addition also to the using 10 females from the fully susceptible laboratory colony in Doso. We amplified 351 or 52 base pair fragments, and we sequenced it. And what we have seen is we did not see clearly like sequences clustering according to phenotype, but what we have observed is all the sequences from the dead mosquitoes, regardless of their country of origin, they cluster together with the sequences from the Induso, which is a fully insecticide susceptible laboratory colony. But what we observed is there is another cluster which contains some sequences from all the 4 countries, which are all from the allied mosquitoes. So when we saw that, we took the predominant sequence from this cluster and we take it to the next step to try to functionally characterize the promoter. So to do that, we cloned the predominant sequence and we cloned one of the dead and we cloned the one from the Induso. We had cloned them into a PGL3-based vector to transfect into insect cell lines, and we did dual luciferase reporter assay to see what happens in terms of promoter activity. So we saw that the promoter or the intergenic region from the resistant mosquitoes, here they call it Sahel alive, is 6 times more active compared to the promoter from Induso. And then to try to find out if there is some potential nucleotides which might be responsible for overexpression of GSTE2, we did promoter delineation. So we kept on removing chunk of the promoter, cloning it, and trying to find out how good it is in terms of activity. And as you can see, when we remove the 3' UTR of GSTE1, which is the gene for GSTE2, this is minus 308 fragment. Somewhere here, there is a reduction in the promoter activity. So gradual removal of the regulatory element result in decrease in activity. But the most striking situation we found was when we removed this particular, when we created this fragment, and by this first one is where we have this pop head box L1 at the transcriptional factor binding site. Then the activity reduced by 64.1%. And when we remove nucleotides encompassing this grainy head transcription factor binding site, the promoter activity was reduced by 70%. So if you look here, you can see that what we have here is between this transcriptional factor binding site, we have insertion of adenine, which is found among those 13 sequences, only alive sequences from all the 4 countries. In addition, there is this transition of thymine to cytosine. So we think this particular changes in the nucleotide is strongly associated with the high overexpression of GSTE2. Likewise, also, when we remove the 5' UTR60 nucleotides, we have only 43 nucleotides out of the 60 from the 5' UTR of GSTE2, leaving transcriptional start site intact. So that rather than combined, we saw completely the promoter activity become completely obliterated. And also from the RNA-seq data, we look using a program created by Rebecca Lobb. We calculated the frequencies of the 6 most important phenotypically important chromosomal inversions, and we show that, as is known, that within the Sahel field data, there is high frequency of 2LA, 2RB, and 2RC chromosomal inversions, with the 2LA peaks in all the countries except for Cameroon, and the 2RB and 2RC within the range of around 80 to 90%. But if you look down, you will see in the case of Induso, the frequency is only less than 10%. So contrary to I can't say blip. I think I just look at it later today. I shouldn't say blip. I would say contrary to the data from before, where if you ask randomly, people tell you within when you go to Sahel, what you see is some Anopheles arabiensis. These days, what we are seeing in those drier regions, what we are seeing is Anopheles colici becoming very, very dominant. And this is not surprising because Colucci is known to have a high frequency of the epidemiologically important chromosomal inversions to NA2RB and 2RC, which have been linked to thermotolerance, desiccation resistance, and environmental flexibility. And we saw that a common a handful of well-known metabolic resistance genes are operating within the Sahel. And if you take them from the data and what we have seen from this work, they are able to confer insecticide resistance to many of the public health insecticides. And also, we have shown that possibly the overexpression of CYP2 is a positive from operational perspective because in a place where there is some clothianidine-based malaria control tools like IRS is being considered, if CYP2 is overexpressed, there is possibility that the mosquitoes will be the products, the malaria control tool will be highly effective. And findings of our studies, we also, once we do, we share with the respective malaria control programs in the countries. I will say thanks to my sponsors, Wellcome Trust, and my line manager, Professor Charles Wanji, and two of the students who helped with the work, technician Helene, and the bioinformaticians in School of Tropical Medicine who helped with the analysis of the RNA-seq data. Thank you very much.
Thank you, Suleiman. You took all your time. You only take one question.
Este es el acertijo de los tornillos anudados, con el que tapan a un montón de lugares. Y aprendanlo bien para que no se escapen al escapar. Se pueden encontrar en ferias o lugares donde hay muchísimas
Thank you very
personas
much.
para
Could you
esta
please,
cosa.
malaria specialist PMI Cote d'Ivoire?
Mucha gente lo
I'm very impressed by the result, all the presenter result in terms of insecticide resistance. But I'm also worried about that because all the country we have in West Africa represented, we have resistance, insecticide resistance. So as a portfolio manager, I'm a little bit worried because what comes next. Because when if you use new generation net, so what comes in next years, we have also resistance. So I would like to know how you manage vector resistance in your country, in your different country, respective country, how you manage vector control with other sectors, such as agricultural sector, where they use much more insecticide and also pesticide.
Thank you very much. I'm not so sure I understand the question, honestly.
Maybe we could
I think you could discuss later
Yeah,
because
maybe
you're
we
out
discuss
of the
later.
time.
I did not understand very well.
You need to introduce the last
We
one.
will discuss with you.
Yeah. Okay, thank you, Suleiman. Okay, the next one will be Carla, presenting on restoring pyrethroid susceptibility in Aedes aegypti, longitudinal study in Mexico.
Good afternoon. Today I'm going to switch gears to a more conventional method of mosquito control, which is outdoor residual spraying in Mexico. So the challenge here is that we have very few molecules available for mosquito control, at least for outdoor spraying. So we have to be very smart in how we use these insecticides, so we can prevent insecticide resistance. So the general model of insecticide resistance selection is that very few individuals in the population carry traits that make them survive under the presence of insecticides. And over many generations, the frequency of these individuals will increase in the population. And then there's an assumption in insecticide resistance management where in absence of the insecticide, the resistant phenotype becomes, it has negative fitness, right? So over time and many generations, the susceptible individuals will be restored in the population and will get susceptibility back. At least that's the main idea. So we tried to do this in the laboratory. We use the bottle bioassays to calculate the lethal concentrations that kill 50% of the mosquitoes. We do a logistic regression and then we get the resistance ratios. So we took a population collected in 2011 and we grew it in the laboratory for 27 generations. If you see the first generations show like 55 for resistance ratios. And as we go through generation after generation, on the F8 we got like 24 resistance. And then by the F2014 we got like 24 resistance. So we know that there is negative fitness in pyrethroid resistance. We repeated these experiments with other mosquito collections and it's the same story. Like pyrethroid resistance declines over the generations. So we tried to test this in the field as Bill Black from Colorado State University and Américo Rodríguez from Centro Regional de Salud Pública in Mexico designed this study in Tapachula, Chiapas. This city is in the border between Mexico and Guatemala. It rains a lot, so there's mosquitoes all year long, and there's always dengue cases reported since 1990 to 2020. This is important because that means that insecticides have been applied to control mosquitoes. First, in the 1960s, to control malaria vectors. DDT was used as in the residual spraying. Then, when dengue started hitting this area, organophosphates were introduced as outdoor spraying. Then in 2000, pyrethroids were introduced, and a single molecule was used for 10 years in a row to control Aedes aegypti. So what we did is we identified a mechanism for resistance called knockdown resistance. We know the mutations associated with this phenotype, and when we track the allele frequency of these mutations over time in collections since 2000 to 2008, we saw an increase in the frequency of these resistant alleles. So we know that pyrethroid resistance is widespread in Mexico. So knowing this, the guidelines for insecticide use in Mexico switched, and organophosphates started to be used in 2012, when chikungunya Zika got introduced in 2013. So our main question here is, we know that they switch from pyrethroids to organophosphates. So here we want to know if they are not using pyrethroids anymore. Is pyrethroid resistance going to decline over time? And will KDR frequencies also decline? So the study design was that we selected some areas in Tapachula, Mexico. We did mosquito collections in 24 sites in different years, starting in 2016 and then finishing in 2020. For each of the collections, we calculated the LC50 for 2 parameters, permitting and deltametering, and also we took a subsample of that and calculated the frequencies for isolation 1016 and the system 5034, which both are associated with ADCD KDR. So our results is that here on each point it represents the resistance ratio of a single site collected point, right? So if you see in the first collection time in 2016, there's like very large and high resistance ratios to permission. 2018 the same. And if you see like there is like sites where there is 5-fold resistance and then 2 kilometers apart there's a site with 70-fold resistance. So there's a lot of heterogeneity in the resistance ratios within the city. We try to explain, to test if this heterogeneity was because of the geographic distance, and we didn't find any correlation. For deltametering, we have the same story. Very large resistance ratios in 2016 and 2018, but I hope you can notice in the graph that there seems to be a reduction in the resistance ratio. The range got smaller and smaller, and in 2019, most of the populations were like lower than 50 for resistance, which is still very high levels of resistance for pyrethroids, but we can see a decline. And it's important just to see that organophosphorus were the only insecticides used during this period. Also, if you see in 2020 and 2021, there's an increase in resistance ratios. So we didn't know, but the vector control program started applying a mixture between neonicotinoids and pyrethroids again. So that explains why we see this increase in resistance ratios again. We didn't have any control over what insecticides are used in the field, right? But we still want to answer the question, like, is pyrethroid resistance going to decline and how fast will this happen? So we decided to use only the collection sites from 2016 to 2019, and we run like a GLM model where we try to explain the mortality as a response to the different doses used in the bioassay, as the 24 different sites used in the study, and the different times of collection. So if you, we can see that the 3 factors explain the mortality, the chances of mortality. And for example, the dose what had the most effect on the mortality, which is expected, but also like as we see like here, like the collections done in 2016, we have to use larger, higher concentrations of insecticide, while after like 6 years of connections, we have to use lower concentrations of insecticide. So holding the dose on the site constant for each month of the pyrethroid removal, the odds of dying were multiplied by 1.4% for permitting and 9.5% for deltametering. This means that for every month that we for each month that we remove pyrethroids, there's an increase in mortality over time, which is really good news, right? Like we can see that pyrethroids can be vector susceptibility can restore. When we check the KDR alleles in absence of pyrethroids, we check the system 5034. Also, like in 2016, we selected the mutation. The resistant mutation is almost fixed in all of the population, and slowly and gradually, these frequencies start to decline. and I apologize because this is not the, for isoleucine is a different response. But for isoleucine 1016, we saw that the KDR frequencies were maintained between 0.4 and 0.8, and they didn't move. They were very heterogeneous, but they didn't show a trend to increase or decrease. So we try to explain like the permission LC50 to test if the permission LC50 was explained by the time of collection, the site, or any of the mutations present in the voltage gated sodium channel. And we saw that the homozygotes for 1016 explain the permission LC50, while for delta methyl, both time and resistance ratio, and homozygote resistance for 15 to the 4 significantly explained. So in summary, I just wanted to leave with this message. Like, you can see that pyritic resistance is declining. We use organophosphate all of this time, and it seems to work, right? LC50 is declining gradually, and I think this information is to be integrated with other methods of control. It will take several years to reach susceptibility, so by itself it's going to be very difficult to work. So also, just to say that introduction of pyrethroids, even in mixtures, it can be very, it can damage what we were expecting in our studies. And with that, I would like to thank Colorado State University, Bill Black, who is my mentor, NIH, who funded this study, and also at Instituto Nacional de Salud Pública, in special, like Americo Rodriguez helped design the study. He passed away from COVID, but I'm very thankful for the team in Tapachula because they were very motivated and they did an awesome work to do all of the work in the field. And yeah, with that, I take questions.
Okay, thank you so much. Okay, I'll ask the first question and then we take one from the room. Okay, so in the case of restoration, you are seeing that the frequency of the KDR is so high, meaning that for that to be successful, you need to intervene very quick to avoid there always to be conflicts in the population before you implement rotations. And in other locations, we are seeing that there's like the level of restoration is like a bit moderate. That will be due to that, and also did you try to see what are the impact of the mutations on some key life type of mosquitoes to see what is happening or what is preventing the restoration to happen. And not from any fitness comparison between the resistant and susceptible ones.
We did some comparisons with, we compared the genomes of resistant and susceptible mosquitoes, and we have found KDR, when we compare the exons, we always find like the KDR mutations always very associated with resistance. But there's also other genes like cytochrome P450s and GSPs, they're always there. We're trying to identify like which markers we can use to complete the model, right? Right now we just have KDR because that was available, but in time I think we're going to start developing other markers.
Sequencing mosquitoes also because the time we were monitoring the frequency of the mutations, we are helped to answer to some of the questions. So we take one of the questions in the room and then we close the session. Yes, two questions.
Thank you. Actually, you are looking at the insecticides for vector control, so the stop of pyretroids replacing by organophosphates. But what's happened with other sorts of treatments? I mean, household products, pest control that probably still use pyretroids. and maintaining a selection pressure on mosquitoes. So do you think that this really low decline actually of resistance is explained by the other source, like use of paratroids? What do you think on that?
Yeah, definitely. Like we didn't have any control of what the vector control was using or what is people using. We know that most of the insecticides sold for domestic use have pyrethroids, right? And at least in Mexico, there was a study where like 85% of the households use these products and they have pyrethroids. And that's why, I mean, these results are very exciting because even knowing that there's a lot of insecticide pressure at the domestic level, we still are seeing this decline. Maybe trying to use products with a different mode of action and recommend that, and that would be helpful, right? To involve the community and try to start them.
Why so?
Okay, last one.
No.
Okay.
Oh, come on.
Good. So thank you for coming and enjoy the conference.
That's good.
Thank you. Nice talk. Thanks. Have time? You want to take it? Thank you. Yeah, I don't have it anymore, but here, I'll give you my email.